Hello friends, today we'll continue discussing dynamic programming, and we'll see another example for which we can use dynamic programming to solve it. Now this example that we will be talking about is the longest common subsequences problem. So what is a common subsequence? A subsequence of this string or this larger sequence is a set of characters in the same relative order as they are in the original string or in the original sequence. But it's not necessary that they be in the contiguous. For example, on the screen you can see that we have a sequence with the characters A, B, C and D. Here you can see the list of all possible subsequences of this string are given. So we can see A is a subsequence of this string, A and B is a subsequence of this string, A and C, A, B, C, A, B, D and so on and so forth. The important thing to observe here is that all the characters in these smaller substrings are in the same relative order as they are in the original sequence, but not necessarily contiguous. For example, you can see this B and D subsequence is maintaining the relative order of B and D in the original string. B comes before D. So this relative order is maintained, but it's not necessary that they be contiguous. Okay, I hope it's clear from the example. So the total number of subsequences that we can have for a given string of length m is 2 to the power m, as you can see on the slide. So we include the null string as well when we are not taking any character from the main input string or the input sequence. What a subsequence basically is, now we'll try to find what does the current problem at hand, that is finding the longest common subsequence from a given set of sequences, basically mean. So the longest common subsequence problem is basically given two input strings S1 and S2. For example, we have shown in the slide here. So given two strings, input strings S1 and S2, the main objective is to find the longest subsequence that appears in both the input strings S1 and S2. So this is the simplest challenge that we are given in this longest common subsequence problem. So in the example in the slide you can see that let's take S1 to be equal to the sequence A, B, F, H and K. So this is one input sequence, and S2 here is another input sequence A, B, H and I. From the observation you can see that the length of the longest common subsequence in this example here is 3. It's shown in the green boxes in these slides, in this slide here. You can see A and A belong to both the sequences, B and B belong to the same to both the sequences in the same relative order, and ABH and ABH here again belong to both the sequences, input sequences in the same relative order, and this is the longest common subsequence of both these two input strings. So the objective here is to find the length of the longest common substring in the or the subsequence in the input sequences or the strings, as well as the subsequence itself. So in this example in the slide that is shown here, the length of the common subsequence, longest common subsequence in these two input sequences is 3, and the sequence itself or the subsequent longest common subsequence itself is A, B and H. Obviously we will be able to solve this problem using dynamic programming only if this problem has an optimal substructure. Let's see if we can find an optimal substructure in this problem or not. As you can see on the slide, now let's suppose we have an input string x with characters x1, x2 up to xm. So m is the length of one of the input sequences, and y is another sequence which has characters y1, y2 and so on and so forth up to yn. So n is the length of the second sequence. Now let's suppose the longest common subsequence that these two sequences have is z, having characters z1, z2 and so on up to k. So let's suppose k is the length of the longest common subsequence of x and y. So if you can see on the slide, let's suppose we have an input sequence x with characters x1, x2 and up to xm. So m is the length of the one of the input sequences, and we have another sequence, that is y, with characters y1, y2 and so on and so forth up to n. So n is the length of the second sequence. And let's suppose we have z, which we refer to as the longest common subsequence of x and y. Let's suppose this z is made up of characters z1, z2 and so on up to zk, meaning that the last character in this longest common subsequence is k, zk. The length is k for the longest common subsequence. So if you see the characteristics of this longest common subsequence, if xm is equal to xn, what does this basically mean? It means the last character of the first sequence is equal to the last character of the second sequence. So xm is equal to xn. Let's suppose it is the case. Then zk equals zm equals zn. What does this basically mean? So if the last character of both the strings matches, then the last character of the longest common subsequence will also match the character that is in question right now. If the last character of one sequence matches the last character of another sequence, then it is obvious that the last character of our longest common subsequence will be the same character, and the remaining portion of the longest common subsequence, that will represent as zk minus 1. So this is the whole longest common subsequence minus the last character. Now this portion, this remaining longest common subsequence, will be an LCS, that is the longest common subsequence of the one input sequence minus the last character and the other input sequence minus the last character. If you look at the example over there, let's suppose x here is one sequence, y here is another sequence, and it is obvious that z here, which is a, b, h and k, is the longest common subsequence of these two input sequences. If you observe, the last character of x matches the last character of y, which is k in both cases. So obviously the last character of our longest common subsequence would also be k, which is here. Okay. Now what about the remaining portion, remaining longest common subsequence? Now this remaining portion I'll represent as zk minus 1. It will be a longest common subsequence of the input sequence x minus the last character and the input sequence y minus the last character. So the remaining subsequence here will be the longest common subsequence of this portion of the one input string and another portion of the second input string. I hope it is clear. The first case is clear, when the last character of both the strings matches. Now the second case here considers the possibility that the last characters of the two input strings do not match. Now let's suppose the case is something like this. If the last characters of the two strings do not match, then zk, means the last character of our longest common subsequence, is not equal to xm, that is the last character of one of our input sequences. Now the case is that the last characters of the two input sequences do not match, and the last character of our longest common subsequence does not match to one of the input sequences. It means that a longest common subsequence of is basically the longest common subsequence of x minus one character and y. Okay. So from the example, let's take the case when our input sequence x is equal to a, b, f and h and k is not there. Similarly, y is equal to a, b, h and I and k is not there, and our longest common subsequence would be a, b and h for these two input strings. Now the case here is the last characters of both these strings do not match, okay, and zk is not, let's suppose, equal to ym. Okay. So here, since zk is not equal to y, let's suppose n, okay, then if Z is the longest common subsequence of y and x, it means that, now the first case is clear, now the second and third cases are common. So let's consider the third case here, because our example is such. If the third case is clear, the second case will also be clear inherently. So let's suppose we have our input sequences x and y having only 4 characters, and this character is not there in our input sequences, and the longest common subsequence obviously will be a, b and h in these two cases. Okay, so we do not have this k character in the input sequence, neither will it appear in our longest common subsequence. So let's consider the case if xm is not equal to yn, meaning the last characters of the two input sequences do not match. Then what does this mean? Zk is not equal to yn. It means the last character of the longest common subsequence does not match the last character of the second sequence, which we are referring to as y. So in our example here, you can observe that yn is I, okay, and z here has the last character, or zk is h. So these two do not match. Then z will obviously be an LCS of x, meaning x the whole string, okay, and y minus n, minus the last character. So we are reducing one character at a time from both these input sequences, unless they are the same. If they are not the same, then we'll keep on reducing one character at a time and try to find whether they have any characters in the particular sequence as common. So now the same characteristic would be followed by another input string as well, which is if xm is not equal to y, if the last two characters do not match here, and the last character of the longest common subsequence is not equal to the last character of the first sequence, then z in our case will be the longest common subsequence for x minus one character, means the last character, and y. And this we can perform recursively in order to find a solution to our problem, that is finding the longest common subsequence. So we can formulate a simple recursive solution to this problem by writing something like this. Given two input sequences x and y, the longest common subsequence, or the length of the longest common subsequence of these two input sequences would be something like this. If the last characters of both the sequences match, or in other words, x of m is equal to y of n, means the last characters here match, then we'll return 1 plus the longest common subsequence of x and y with last characters truncated in for both the input sequences. In this case, for example, in the example above, if we see at these two input sequences x and y, the last characters here do match, okay, k and k. Okay, so we have found that the length of the longest common subsequence for x and y in this input case here would be 1 plus the length of the longest common subsequence in the remaining input sequences. So same thing will perform recursively. In case the last characters of the two input strings do not match, then we'll return the maximum of the longest common subsequence of x minus one character and y as it is, and the maximum of the longest common subsequence of one sequence minus one character at the end, comma the second sequence as it is, and the LCS of the first sequence as it is and the second sequence minus the last character. So we'll try to find a match between the characters by decreasing the length of the two strings, input strings, alternatively. Now let's see how it works in case of recursion here. So let's suppose our input sequences are S1 is equal to A, X, Y and T, and S2, the another input sequence, is A, Y, Z and X. Then the call to that function that we just discussed, the first call would be LCS of A, X, Y, T and A, Y, Z, X. So this is the first call. Now we'll compare, obviously the last characters here, T and X of the two input strings do not match. So we have two options. One would be to find the longest common subsequence of the first input sequence as it is and the second sequence minus the last character. Here you can see we have deleted x in one of the cases, and the longest common subsequence of the first sequence minus the last character and the second sequence as it is. So, we will have to find, since the last characters do not match, it will be the LCS would be the maximum of LCS of this and LCS of this, the length of the LCS, longest common subsequence. We will proceed with the left subtree first. So, it will be LCS of the left sequence as it is and the right sequence minus y character. So, it will be the z will be removed in this case here. Similarly, for the other case, the left sequence would be deleted with the last character and the right sequence would be as it is, as it came from the previous call. So, this is just a partial recursion tree of our example here. Now, obviously, you can observe that these two calls here are common in these two branches of our partial recursion tree. Now, this obviously means that this problem has an overlapping substructure. You can see we are trying to find the LCS of AXY and AYZ in one branch, in this left branch, as well as we are also finding the same thing in the right branch. So, we are repeating certain problems, and that is where dynamic programming comes in play. So, dynamic programming tries to exploit this case and solves this repeating problems once and reuses the result. So, we will see how we can use dynamic programming to kind of provide a solution to this problem. Again, if we look at the naive approach, that is using pure recursion, you can observe that it will take order of n into 2 raised power m time, where n is the length of one sequence and m is the length of the second sequence. Why is that so? It is because there are 2 raised power m subsequences of x, one input sequence, and there are n number of characters for the second sequence. So, we will have to compare whether each of the subsequences of one sequence, one input sequence, matches somewhere at some position in the other sequence. So, we will have to compare 2 raised power m subsequences with at n positions for the second sequence. So, that is why it is order of n into 2 raised power m time. So, obviously, the dynamic programming approach should yield a better result or should be more efficient than this by reducing the computations that are required, that is the objective. So, we will see how we can do that. Dynamic programming in our case right now will be considering the bottom up approach. Obviously, there are multiple approaches of implementing dynamic programming solutions, be it a bottom up approach, be it a top down approach, and so on and so forth. So, for the time being, we will be dealing with a bottom up approach for our solution to this current problem. So, as you can see on the slide, let us suppose we have two input sequences S1 and S2 being AXYW and AYZPW respectively. We are maintaining these sequences in two arrays, okay, namely S1 and S2. The indices are 0, 1, 2, 3 and 0, 1, 2, 3, 4. So, the length of one sequence is 5 and the length of another sequence is 3. Now, for a dynamic programming solution, we will simply maintain two-dimensional array named LLCS with dimensions equal to, let us suppose for example, we have the length of one sequence is m and the length of another sequence is n. We will maintain a two-dimensional array with dimensions m plus 1 cross n plus 1. Okay. So, this will be the dimensions of our array that we will have to maintain for generating the result. So, you can observe that the input sequences in our example are of length 4 and 5. So, we have maintained a 5 cross 6 or a 6 cross 5, it is not necessary how the ordering would be. You can treat this to be sequence number 1 and sequence number 2, or this to be a sequence number 1 and sequence number 2. So, in either case, we will maintain a two-dimensional array of the specified dimensions as I just told you. Let's suppose this is for S1 and this is for S2. Okay. Now, what this basically means is we are trying to find the length of the longest common subsequence considering 0 characters from sequence 1, okay, and considering 0 characters from sequence 2. So, what will be the length of the longest common subsequence in case we are considering 0 characters from first sequence and 0 characters from the second sequence? Obviously, it will be 0. So, we have stored here 0. Similarly, this here means we are considering 0 characters from sequence 1 and 1 character from sequence number 2. Obviously, in this case again there will be the length of the longest common subsequence would be 0. Same here, if we are considering 2 characters from first 2 characters from the second sequence and considering 0 characters from first sequence, in this case again the length of the longest common subsequence would be 0. Now, same applies for this row as well. What this basically means here is we are considering 0 characters from the second sequence and 1 or the first character from first sequence. Again, the length of the longest common subsequence would be 0, and so, this applies to the first row and the first column in our case. So, we have maintained this as the base case for our solution, on top of which we will build a solution using dynamic programming. So, in order to build a solution using dynamic programming for our current problem, we will use 2 indices for this matrix that we just generated, or the two-dimensional array that we just generated, and we will call them as I and j. So, these are the 2 indices that we will be using to manipulate this two-dimensional array in order to build a result. Okay, so based on these base cases that we have just filled in, which is zeros, this first column and the second column, which basically means that we are considering no character from one of the sequences. In that case, obviously the longest common subsequence, the length of the longest common subsequence would be 0 if one of the sequences is taken to be as null. So, that is what this basically represents. So, and we will use them as the base cases to build our solution, as you will see in a moment. We will use 2 indices labeled I and j for the 2 input sequences to build our solution, and we will start I and j both at 1 and 1. Let us suppose if this is taken to be equal to I and j for the time being, then this cell here would be labeled as or indexed as I minus 1 comma j. This one here would be I comma j minus 1, and this one here would be I minus 1 and j minus 1. So, this is a simple relationship that you can observe while building our solution. We will use this relationship. So, we will continue with this. So, we will use 2 indices I and j for the 2 input sequences starting from 1 for both the cases. Now, we will use these conditions to build our solution, and these conditions are something like this. We need to check the character pointed by I minus 1 for the first sequence if it is equal to the character pointed by j minus 1 for the second sequence. So, let us, in our example, let us try to find out what this basically means. We can observe that I here is equal to 1. So, I minus 1 would be 0. So, S1 of 0, which is A, and S2 of j minus 1, j also is 1. So, 1 minus 1 would be 0. So, S2 of 0, which is also A. Now, in case if S1 of 0 is equal to S2 of 0, okay, then the longest length of the longest common subsequence at I comma j is equal to the length of the longest common subsequence at I minus 1 and j minus 1 plus 1 character, because since 1 character matched, so we will add 1 to whatever we have previously found. Okay. So, if you observe, you can see that A equals A in our case. So, it will be LLCS of I minus 1 comma j minus 1 plus 1. So, since I is 1 and j is 1 and 1 minus 1 is 0 and 1 minus 1 is 0. So, LLCS of 0 plus 1, which is 1. So, for the current position we have filled a value of 1. Now, let us increment this j to the next position, and if we observe here the same condition that we used earlier, if S1 of I minus 1 is equal to S2 of j minus 1, then LLCS of I comma j is equal to LLCS of I minus 1 comma j minus 1 plus 1. Now, in case this is not the case, then LLCS of I comma j is equal to the maximum of LLCS of I comma j minus 1 and LLCS of I minus 1 comma j. Now, to make it simple, now let us suppose we are here I comma j. Now, in case the characters of the two sequences indexed by I and j match, then we simply need to add to whatever is diagonal here, to whatever is LLCS of I minus 1 j minus 1. Okay. The value here would be 1 plus the value whatever is here. So, the diagonal value, in case the characters match. Now, in case they do not match, then what do we need to do? We will have to see for this cell here, if the characters do not match, then the value here would be the maximum of this character, this value here and this value. So, this is LLCS of I minus 1 comma j, and this here is LLCS of I comma j minus 1. So, the maximum of these two would be used to fill in the value for this cell here in case the characters do not match. So, let us proceed with our earlier example. So, for the first case we found when I and j were equal. So, the characters when I and j were equal to 1, the characters for S1 and S2 matched. So, we would have to consider 0 plus 1, the diagonal case, and the value would be 1. Now, when we increment j to the next character and we see that x and a for these two sequences they do not match, then it will be this, the value here would be maximum of 0 and maximum and 1, maximum of 0 and 1, which is 1. So, we have stored 1 here. Now, similarly, we will increment this j by 1 again, and we can easily observe that y is not equal to a. So, again the value here would be maximum of 0 and 1. Okay. So, and we will keep on doing the same thing. Again we will increment j, we will see that this w is not equal to a. So, the value here is maximum of 0 and 1. Now, let us move ahead for the second row. So, we have incremented I by 1. So, I is 2 now and reset j to 1. So, now if we see the characters again pointed by I minus 1 and j minus 1 for S1 and S2 do not match for this case. So, it will be maximum of this 1 and this 0, which is 1. Similarly, for x and y, next case again the characters do not match. So, this value has been generated by taking the maximum of this 1 and this 1, and so on and so forth. In this case right now, where j is equal to 3 and I is equal to 2, you can simply observe that the characters match. So, y is equal to y. So, the value for this case here, the cell here would be the diagonal value plus 1. So, it will simply be 2. I hope it is very much clear. And again, if we increment this j by 1, w and y, they do not match. The value here would be maximum of 1 and 2, which will take as 2, and we will keep on proceeding the same way, and this is the final matrix that was generated by following this approach. So, you can observe the last character here w and w matches, and at that point of time it will be 2 plus 1, which is equal to 3. That is what we have stored. So, the length of the longest common subsequence for these two input strings would be LLCS of m comma n, where m and n are the lengths of the two input sequences respectively. The length of the longest common subsequence for our input sequences would be length of S1 comma length of S2. So, LLCS of length of S1 comma length of S2, which is this cell here. So, this will be our solution in case we just want the length of the longest common subsequence. Now, So let's suppose we not only want to find the length of the longest common subsequence here, but also the subsequence itself. How do we kind of do that? Do we need to maintain some intermediate information or some additional information in order to be able to generate that subsequence later on or not? That's what we'll be talking about right now. While we were generating our result, the first change that we got was when the first characters matched. And how did we generate it? We got this value by considering the diagonal here. Okay, the next increment is here. And how did we get that? We got that by considering the diagonal value here. So we incremented the diagonal value, this value. We incremented this value to get this 2. Similarly, how did we get this 3? Finally, we incremented this diagonal value. Okay, so we incremented this 2. But where did we get this 2 from? We got this 2 from this cell. So it is obvious that if we know the direction of how we generated these values, we can reconstruct our sequence. So if we somehow are able to store this information while we were generating these results here, as you can see, we'll be able to reconstruct our solution and find subsequence itself as well. Now, as you can see here, this is a small piece of code which helps us maintain the intermediate solution as well. So we have changed the code that we just used earlier to build our result. We added some statements in there. So in order to generate the subsequence as well, we'll maintain some other additional information so that we'll be able to rebuild our solution later. So if you look at the slide, we have added some statements to our previous snippet of code through which we generated that two-dimensional array, which is this statement here, wherein we are using an additional two-dimensional array named solution, okay, with the same dimensions as that of the LLCS. And we have also added this small portion of code. Now what we are doing here is, whenever we find that the two characters are matching at a point indexed by I and j, whenever they match, we'll store a character named d, okay, at the same position in some other array named solution. Now what this basically indicates is that we have found our solution by considering the diagonal element at this particular point of time, or at this particular index by pointed by I and j. So we have added 1 to the diagonal, okay, in this case. Now in case they do not match, in case these two characters do not match pointed by I and j, then if the LLCS of I comma j is equal to LLCS of I minus 1 comma j, okay, so if the two characters match considering if the two characters match considering the first string as it is and the second string minus the last character, then it means we have considered the top cell in the current scenario to generate the value for LLCS for the current I and j index. So we'll use u to be stored in this solution array. We'll later on see how we'll use this u. And in case it was not that we needed to decrement I, okay, decrement I to get our solution, in case it was j to be decremented, okay, in case it was j to be decremented, then we'll store solution of I comma j to be equal to L, okay, means left. We considered the left value to generate the value for the current I comma j index. We'll see how it is done. Now as you can see in the slide, from the previous example, this is the LLCS array that was generated. Now if we use the intermediate statements for maintaining a solution array as well, and we use those L, U and T characters, okay, so then the final state of this solution array would be something like this. Now as I earlier told you, this 1 was generated because we considered the diagonal element I, or we incremented this diagonal element. So we'll, for this position, we'll store d. Now at this point we used the diagonal value to generate our result, okay. Similarly at this point we used the left value, okay. Similarly at this point we used a diagonal value. Similarly at this point we used the top value. that is why there is t here. At this point as well, we use the top value to generate our result, that is why this is t here. So finally at this point we use the diagonal value, and that is why it is d here. So using these two arrays, these two intermediate arrays, this gives us the length of the longest common subsequence, and following these sequence of characters will help us regenerate the actual solution. And how do we do that? Starting from the last position of this solution array, we'll scan these characters. So for example, here it is d, so we'll go diagonally, so we'll go here. In addition to this, before we move diagonally, we'll print a character at this I or j. So given these two-dimensional arrays that are maintained intermediately, the LLCS and the solution, the LLCS, the last element of this LLCS array will give us the length of the longest common subsequence, and we'll use the last character or the last element in this solution array to start building our result, something like this. Now we scan the last element in our solution array, and we see that it is d. It means we have to move diagonally. Now since it is d, we'll also display here S1 of I or S2 of j. Solution of 4, 5 is d, then it is obvious that S1 of 4 minus 1, which is 3, is equal to S2 of 5 minus 1, which is 4. So if this is the case, if this is d for 4 and 5, then it is implicit that S1 of 3 is equal to S2 of 4, and we can display either of the two. Either we display S1 of 3 or we display S2 of 4. So we'll build our solution by considering one of the characters, either S1 of 3 or S2 of 4. Now after we store this character, we move diagonally, okay, and we see that we have a t here, and we do not need to display a character in case it is a t character, okay, and we'll move to top again because it was t earlier, and we encounter another t. So using this t, we'll move again top without displaying a character, and we find a d here. As soon as we encounter a d, it means that S1 of 1 would be equal to S2 of 2, okay. So we can display either S1 of 1 or S2 of 2, 3 minus 1, 2 minus 1, okay. We are considering minus 1 here, for I and j. So we display another character in our sequence, in our longest common subsequence, reverse in reverse order, okay, and we move diagonally, and we see that it is an L. So we do not need to display a character for this character, in this case L. We do not need to display a character in this case L, and we move left and we encounter a D. So here I is equal to 1, j is equal I is equal to 1, j is equal to 1. So we can display S1 of 0 and S2 of or S2 of 0 to finally build our result, and finally we just end the solution or exhaust the indices of the solution. Now this is how we do this. Starting from D, we will use j index for S1, okay. So j here is 4, okay, 4 minus 1 is 3, so we'll display W, okay. So this is W has been displayed because it was D here. So we move left, I is equal to 4, j is equal to 3, we find a character T, so no display, and move towards the top. Again we encounter a T, no addition to our solution, so we and we move towards the top. Now we find a D again, and we see that I is equal to 2 and j is equal to 3, 3 minus 1 is 2, so index 2 for S1 will display Y, okay. So this is Y, and then we move towards diagonally, and we see an L, so no character needs to be displayed. Now again we see an L, we need to move left, so we encounter a D at this point of time. I is equal to 1, j is equal to 1, 1 minus 1 is equal to 0, so we'll have to consider S1 of 0, which is A, and we display that result. And finally we move towards the left and we find 0, and we just stop over there, and the sequence of characters that we just stored, whenever we found a D in the solution array will form the actual solution. Okay. So, the length of the longest common subsequence is 3 and the sequence itself is A Y W for this example. And this piece of code here is the complete algorithm using dynamic programming for formulating the longest common subsequence solution. And this is the piece of code in case you want to use two arrays, that is the LLCS and the solution array. This is for initialization, filling in the zeros for the first row and the first column, and then using the dynamic programming part here, the conditions in case S1 of I minus 1 and S2 of j minus 1 are the same, then we just need to increment 1 to the diagonal element and store D in the solution array. In case it is not the case, then we will have to use the maximum of LLCS. I will write here, it is not written. So, LLCS of I comma I and j minus 1. And we also need to maintain T and L in the solution array accordingly. And in order to generate our result from the solution array, this piece of code will be used. Okay, I demonstrated it already. So, in case dir is 0, we just stop. In case it is not, so starting from the last cell here, x and y, we are using two indices x and y to generate our solution. So, if the solution of x comma y is equal to D, then we just need to add this character pointed by x minus 1 to our answer, and we decrement x and y, okay, both x and y. In case it is left, it means y needs to be decremented. In case it is t, so x needs to be decremented, and so on and so forth. So, this is where we end today for the current example using dynamic programming for solving the longest common subsequence problem. This was a small demonstration, and the piece of code that you can use is shown in the slide, plus some additional change that you need to make here. I hope it is clear in the previous thing that I just told you. So, we will continue with the dynamic programming in the next class as well. We will do our last example when we will deal with the all pairs shortest path problem. We will try to find a solution using dynamic programming to that problem as well, and hopefully we will see you next time. Thank you.